In today's short video, we're going to talk about two concepts. One is transition metal ions. Transition metals we've been ignoring because they don't fit into these patterns that show us from the periodic table exactly what their charge is going to be when they become an ion. But they do make ions, and so we're going to talk about how to deal with that. And then the second thing is we don't know how to name covalently bonded compounds, in other words, molecules. There's a way to do that, and we'll talk about that today too. For lots of transition and post-transition metals, in fact for most of them, more than one charge is possible. So what are the transition and post-transition metals? Well, they're outlined here in red on this table. So it includes the transition metals, the scandium through zinc, and then lanthanum through mercury columns, and then the lanthanides and actinides that are down here way on the bottom. But then it also includes these things that aren't exactly transition metals, like indium, tin, thallium, lead, and bismuth. They are post-transition metals. For all of these things, there's more than one possible charge. They're always going to be positively charged, though. So how do we know what their charge is? Well, in most cases, we have to rely on either the name or the formula to tell us the charge. Here's how it works with the formula. The formula has to show a charge balance. It has to reflect a balance between the pluses and the minuses. So the anion's charge can help us with that. Here's an example. CuCl. We know that the chloride ion is a 1- ion. Since there's one copper with every one chloride, we don't see any subscripts there, that means the copper must match that, so this must be a copper 1+ ion. The charge must be 1+. Now in this copper chloride, we see a different story. Chlorine, of course, has to be -1 because it's a halogen, group 7. They're always -1. But this time we see that there are 2 chlorines for every 1 copper. So that means the copper must be balancing 2 minus charges, so the copper must have a charge of 2+. You can kind of think of this as reversing the charge swap that we did to create the formulas in the first place. This 2 gets reversed up here, and that tells you that it's 2+. It isn't always going to work that simply, but many times it does. Here's an example. What's the charge on the iron ion in Fe2O3? You figure this out, and I'll bring you back an answer. Well, if we think about oxygen's charge, oxygen is 2-. There's a 3 subscript on the oxygen, which tells you that all told we have 6 minuses in here. 3 times 2-. So the iron that we have here must give us a total of 6 pluses. But there are 2 of them, so that means each one is 3+. So that tells us that the iron ion is 3+. What's the charge on this copper ion in copper nitrate? You figure this out, and I'll bring an answer. Well, the nitrate ion, NO3, if we look that up on our polyatomic ions, we see that it's a 1- charged ion. Now, since there are 2 of them, that means 2- total. So the copper that I'm dealing with here must balance 2 negatives, so it must be 2+. If we don't have a formula, but we have a name instead, we use something that's called the stock system. The stock system uses a Roman numeral in parentheses after the name of the metal to show what the charge is, and it's always a cation, so it's always positively charged. So here are the Roman numerals that you'll see. 1, that's a 2, 3 lines is a 3, an I and a V, that's 4. Occasionally you might see a 5. Once in a while a 6, which is a V followed by an I. So just a review of your Roman numerals, because you probably don't use those too often. Here's an example. Iron 2. Because that Roman numeral is there, it's a 2, and because I know this is a cation, the ion I'm talking about is Fe2+. Or iron 3 chloride. Well, if I'm going to write the formula for this ionic compound, I start out knowing that it is Fe3+ because the Roman numeral 3 tells me that. Chlorine is column 7, that's always a 1-. So when I do charge swap, I will end up with FeCl3. You try one. What's the charge on the copper 2 ion? Well, it's very simple. Just look at the Roman numeral, and that's the charge. Cu is copper's symbol. It's 2+ because of the Roman numeral 2. write the formula for chromium 3 nitrate. Stop the video and give this a try, and I'll show you the answer in a bit. Well, chromium symbol is Cr. The Roman numeral 3 tells me that this is a 3+ cation. If I look up nitrate in my polyatomic ions, I find out that it's NO3 and it has a 1- charge. So then I do charge swap. Cr doesn't get a subscript because the charge on nitrate is 1. Nitrate gets a subscript of 3. Because it's a polyatomic ion, I enclose it in parentheses first, then I put the 3 down there. So there's the formula for chromium 3 nitrate. Try this one. It's the formula for lead 4 oxide. Lead 4 means 4+ charge. Oxide, well, that's oxygen. Oxygen's in the 6th column and they make 2- ions. So when I do charge swap, the lead gets a 2, the oxygen gets a 4. Now in an ionic compound, when I have subscripts like this that could be reduced to lower terms, I always should do that. So instead of Pb2O4, I'm going to write PbO2, and that's my formula. What's the charge on the titanium ion in TiO3? Be careful here, this one's a little tricky. Well, I'm going to try the reverse charge swap thing. If I do that, that would indicate, by putting this 3 up there, that this is titanium 3+. But that would be wrong. In fact, because oxygen has a 2- charge, and there are 3 of them, that means the oxygen provides a total of 6 minuses. There's only one titanium, and that titanium has to provide all 6 pluses, and so this is titanium 6 oxide. What's the name of FeCl2? Well, to know the name, I have to write down what is the Roman numeral that goes after it. That means I have to figure out what its charge is. Iron is bonded here to chlorine ionically. Chlorine is 1-, and there are 2 of them. So that means 2 minuses for chlorine. They have to be balanced by 2 pluses for the iron. So this is iron, Roman numeral 2 to indicate the 2+, chloride. Now there are 2 exceptions that we're going to deal with in this class to this rule that transition metal ions always have multiple charges. One is the zinc ion. Zinc, when it makes an ion, it's always going to be a 2+ ion. We don't have to look for a name. We don't have to put a Roman numeral in there. We don't have to analyze what the anion's charge is. It's always 2+. And silver is always 1+. So these are the 2 transition metals that we're going to see in this class that are consistently charged. Our next topic is naming molecular compounds. Because a molecule is a unique particle that didn't exist before, it's more than just a ratio. So in ionic compounds, like we saw in one of the examples, Pb2O4, we reduced that to PbO2 because really it's just a ratio of how many lead ions to how many oxygen ions. But a molecule isn't like that. If I have, for example, H2O2, which is hydrogen peroxide, I cannot turn this into just HO because that's a molecule with exactly 2 hydrogens and exactly 2 oxygens. It's not just a ratio. So we have to use exact numbers, and our naming system has to account for the fact that we need to use exact numbers. Well, here's how we do this. We make use of some Greek prefixes. They're word parts. We attach them in front of the names of the elements in a molecular compound to tell what the subscript is. If the subscript is mono, we use 1. Di, 2. Tri is 3. 4 is tetra. Penta, like a pentagon, is 5. Hexa, like a hexagon, is 6. Hepta is 7. Octa, like an octopus, is 8. Nona is 9. And deca, like a decade, is 10. So there are more of these things, but we'll just work with 10 of them in this class. So the prefix precedes the name of the element with that subscript. In other words, you put it in front of the element name. The last element listed ends in "ide" when you're naming a molecular compound, just like in an ionic compound. And the Prefix mono, we usually don't use that. When it refers to the first element in the compound, we don't say mono. It's only used for the second element in the compound. And unless it's oxygen, we still usually don't use it. So for example, if I had NO2, I wouldn't say mononitrogen dioxide. We just don't use mono when it's the first element. Okay, so here's an example. NO. There's no subscript on nitrogen, and there's no subscript on oxygen. So you might think mononitrogen monooxide. But we don't use mono for the first element, so it's just nitrogen monooxide. And if there are two vowels in a row, usually one of them gets dropped just to make it sound a little smoother. So nitrogen monoxide is how you'd say that. Here's another one. NO3. Subscript on nitrogen is 1, so we just write nitrogen. Subscript on oxygen is 3, so we would write tri before we wrote oxide. Nitrogen trioxide. So another one, this is a compound that used to be used for dry cleaning. Subscript on carbon is 1, so we just write down carbon. Subscript on chlorine is 4, and the word part for 4 was tetra. So carbon tetra chloride is the name. Try this one. Name N2O4. The subscript on nitrogen is 2, so we start out with dinitrogen. And the subscript on oxygen is 4, so we finish with tetra ox, and then we end in ide, tetraoxide. Or just tetroxide. Name this one. Subscript on sulfur is 1, so just sulfur. Subscript on oxygen is 3, so we start with tri, and we end with oxide. Name this one. Well, most people would just call this water, but the technical name for it is dihydrogen. And then there's a subscript of 1 on the oxygen, so monooxide or monoxide. Now here's an important note. Don't use these prefixes when you're naming ionically bonded compounds. So PbO2, you would not say lead dioxide. How do you know if it's ionically bonded? Well, the quick way is look for a metal. If there's a metal in the compound, prefixes are not going to be part of it.